Chi-square test for homogeneity. In the previous topic, the use of a chi-square test to describe the distribution of a categorical variable in a population was discussed. Many times, there will be a need to determine if the distribution of a categorical variable is the same for multiple populations. This type of test is called a chi-squared test for homogeneity. With these types of significance tests, the data will require a two-way table. The chi-squared test for homogeneity is almost exactly the same as the chi-squared test for goodness of fit. Meaning number one, the conditions are the same. It has to be random, meaning the data has to come from a well-designed simple random sample. For the 10% rule, when sampling without replacement, the sample size must be less than or equal to the population size divided by 10. And by the law of large counts, all expected counts must be greater than or equal to 5. Meaning number two, the expected values can be found the same way, but must account for the two-way table, resulting in the expected counts being equal to the row total times the column total, all divided by the table total. Meaning number three, the chi-squared statistic formula is still the same. And chi-squared is equal to the sum of the observed data minus the expected value or expected counts quantity squared divided by the expected value or expected counts. And remember, we have the I in subscript, meaning that depending on how many total options are in the two-way frequency table, we will have to add all of them up. Meaning number four, the p-value is found the same way. However, the degrees of freedom are calculated using the following formula. The degrees of freedom is equal to the number of rows minus 1 times the number of columns minus 1. Let's try an example to see how this works. A university wants to investigate if there is a difference in the proportion of students who own a car between 3 different majors: business, engineering, and the arts. They've randomly sampled 100 students from each major and recorded whether or not they own a car, and the results are shown in the two-way table below. So business, we could see that 40 of them had a car and 60 did not. Engineering, 60 had a car and 40 did not. In art, 20 had a car and 80 did not. That makes the total for the car column being 120. The total for no car is 180. And the total from each school, which is stated in the problem, is consistent. There are 100 across each of those majors. So then the total is 300, and it's found by adding up everything within the last column as well as everything in the last row. At a 1% significance level, test whether there is sufficient evidence to conclude that the proportion of students who own a car is different among the 3 majors. Now remember, in order for a chi-squared test to occur, it must be random. It was definitely done randomly among the 3 majors, so it's a well-designed simple random sample. For the 10% rule, when sampling without replacement, the number of people, 300, that we have is less than or equal to the total population divided by 10. And usually at a university, there are quite a few students, so 300 is definitely less than or equal to 10% of that school population. And the third condition with the law of large counts, for the chi-squared test, all expected counts are greater than or equal to 5, and that is definitely true for our data. So let's write our hypotheses. For our null hypothesis, we want the proportion of students who own a car being the same for all 3 majors. And then the alternative hypothesis will be the proportion of students who own a car is different for at least 1 major, making them not all the same for the 3 majors. The next step is to calculate the expected values or expected counts. And this value was found by multiplying the row total by the column total all divided by the table total. So if we do that for each cell, business, we had the row total, business with a car, I should say. The row total for a car is 120 times the total for business, 100, and divided by the total here, 300. And if we do the multiplication and division, we end up getting 40. And the same holds true for engineering and art that have a car. And then for no car, we have 180 times 100 divided by 300, and we get 60. And again, because these are the expected values or expected counts, these are what we expect them to be in theory. So they will all be consistent and the same. So we will get 60 for every cell within the no car column. The next step is to calculate the chi-squared value using the formula observed values minus expected values, that quantity, squared, divided by the expected values for that item. And notice, since we need both observed and expected, we can adjust our table and write in the observed for business with a car was 40 and the expected for that was 40. For engineering with a car, the observed amount was 60 and the expected value was 40. And for art, the observed was 20 and the expected is 40. And similarly, we can fill in the data for no car. Observed with business students that had no car was 60 and the expected is 60. Observed engineering students with no car was 40, expected was 60. And the observed art majors with no car was 80 and the expected is 60. So now let's substitute these into our formula. So now let's work on calculating our chi-squared using the formula. So for business with a car, we will have 40 minus 40 squared divided by 40. We will have 60 minus 40 squared over 40. And then we'll have 20 minus 40 squared over 40 for our first set of terms that we are adding up for the summation. And now let's do the formulas for the data that have no car. That'll be 60 minus 60, quantity squared divided by 60, plus we'll have 40 minus 60 divided by 60, and the 40 minus 60 needs to be squared. And then we'll have 80 minus 60 quantity squared over 60. And if we type this into a calculator and evaluate, we get an answer of 33.3 repeating. The degrees of freedom in this problem are 3 minus 1, which is 2, times 2 minus 1, which is 1, and 2 times 1 is equal to 2. If we use a calculator, we can find that when chi-squared is equal to 33.33, if we round it off to say the nearest hundredth, and the degrees of freedom are 2, we are going to get a resulting p-value. And let's actually substitute that into a calculator and go about this process. And we can do this using the TI-84 plus CE as well as a TI-89. In the TI-84 plus CE, the chi-squared, the desired chi-squared test is found in second variables, so distribution menu. And then if we scroll down, there's the chi-square CDF that we had talked about on an earlier slide. Our lower bound is that chi-square value that we have. Our upper is the total number of samples that we have. So that's 300, and then our degrees of freedom is 2. And if we paste it and calculate, we get about 5.79 times 10 to the negative 8th power. So that's a really tiny number. So 0.000000579. And then this p-value of 0.000000579 is much less than the alpha level value of 1/100th. Therefore, we can reject the null hypothesis, and this means that there is sufficient evidence to conclude that the proportion of students who own a car is different among the 3 majors.